so I can repeat what I am supposed to say. I think recording is on. All right. Good morning again, everyone. And again, welcome to Math 174. This is our first formal session. So for today, we'll be going over actually for the week, we will be going through module number 2. So this is already available via Canvas. So pwede niyo siyang i-download. This has several packages to it. So it has the study guide, ano yung mga dapat yung basahin, or what are the learning objectives for the week. It also has the main discussion for the week. So nandito yung text na kailangan nating i-cover. All the examples are here so that you don't need to jump to another resource. But if you want to have a more full-on and a more detailed discussion in relation to other topics, you can see everything in the module in the work text. Though I guess I just copy-pasted things from the work text and put them into the module para lang centralized na yung babasahin nyo. And also, at the end of module 2, you will see lab exer 1.1. So this is the expected output for this week. Pero ang deadline niya would be Monday, right before midnight, so that you guys will have some time to work on it after nating magawa yung discussion on the lecture. And you will also have your laboratory sessions para mag-guide kayo kung paano siya gumawa. So if you have questions, or kung talagang napakadami yung kailangan gawin for one particular week, just devote the 3 hours on Monday to work on lab exer 1.1. This is the first half of exercise 1. So at the back of our mind, when I ask our lab instructors to prepare this exercise, dapat siya ay good for 1.5 hours. So you can do it on Monday. You can ask guidance from your lab instructor. Di ko alam kung gaano kahaba yung extent na tutulungan nila kayo. Of course, it should be short of giving you the final answers. So they'll be more than happy to answer your questions. So take advantage of those lab sessions, and then you'll have a couple more hours to finalize your work. Make sure to submit them on Canvas right before midnight. And please allot some time for uploading your work in Canvas. So yeah. Okay. So wag niyong isagad na 11:59 kayo magla-log in sa Canvas. Take allot some time for uploading and some possible glitches. All right. So let's take a quick look at module 2. So again, as I've mentioned, do not skip the before you proceed part because this is the study guide. So it says here all materials here would be for the 20th to the 24th of the month. So ito yung main reference natin. You'll have your synchronous lab session for module 2 on the 27th. And as I've mentioned, sa gabi rin on 27 yung deadline. So what are expected from us after this week? So you should be able to state the Weierstrass first approximation theorem and the unisolvents theorem. These are two major results for numerical analysis. Discuss the significance and implications of these theorems, and then derive the Lagrange form of the interpolating polynomial relative to a given set of data points, along with error estimates. So perhaps we can do objectives 1, 2, and probably half of objective 3 today, and then the rest will be done on Thursday. Okay. So here are suggested reading materials. You can consult modules 3 and 4 from last semester. I provided the link in the module. Or you can just stick to our module or to the work text. Okay. So in discussing this, maybe I'll switch to a Beamer presentation para medyo mas malalaki yung fonts. So this is actually the presentation I used last 2015. So hindi ko na binago. Hindi na ako nagpanggap na gumawa ako ng bagong slides for this semester. Because essentially what I want to talk about today is covered in this set of slides. But let's start. So what do we want to do in interpolation? So there are several instances in the real world wherein we cannot use the tools that we learned from our calculus courses. Remember, sa Math 36, ang daming application nating 36 and 37, ang daming applications on derivatives, integrals, sa Math 17 or your algebra courses, maraming applications. But if you notice, these applications or textbook applications require you to have a function, and usually these functions must be well behaved. But unfortunately, in the real world, we do not get a function right away. What we get probably would be a set of data points, a discrete set of data points. So halimbawa, gusto nating i-model yung outbreak ng isang epidemic sa isang lugar. Ang makukuha nating data from the real world is not a function P of t representing the number of infected individuals on time t, pero makukuha natin is something like this. We will get a tabular set of data, right? So this just tells us na at day 0, there are no deaths yet. After 10 days, there are 8 deaths due to the disease, and so on. So ito yung makukuha nating data from the real world. And if we will rely on things that we learn from calculus, parang wala tayong pwedeng gawing masyado on this data set because we were trained to work with certain nicely behaved functions, right? So kaya lang ang problema, hindi nga ganoon yung nangyayari sa tunay na buhay. Usually we just get at most a discrete set of data such as these. Or halimbawa, di ba sa okay, so also halimbawa, kung maalala nyo sa Math 36, usual problem or classic problem is to optimize, say, your sales for a particular product, right? But tatanungin nyo, sir, okay, yan yung application, pero paano ko siya ma-apply sa tunay na buhay? And you're right to question that thing kasi in the real life, we don't get a function for the revenue. Kasi hindi ganun yung nakukuha nating data sa tunay na buhay. So we cannot just find the derivative of a function, equate it to 0 to get the maximum. Or in some cases, you want the minimum of that function. Because what we get, say, from real-world data, instead of a function that models the revenue for a particular product, we get a set of data points. Say, at 70 pesos, I'll be able to sell 1,250 units of whatever product or commodity I'm selling. If I'll sell it at 82 pesos and 50 cents, I'll be able to sell 750 units. And then how do you use this data in order to get the maximum revenue? Unfortunately, Math 36 doesn't or did not teach us that. Kasi kailangan meron tayong nicely behaved function. Actually, what we need there is a differentiable function. Get the derivative, equate to 0 to get the critical numbers, and after that we'll get the maximum and the minimum. But again, that's not how data in the real world behaves. So usually discrete set of data lang yung nakukuha natin. So for the first part of Math 174, we'll try to develop some ways in order to get a polynomial or a function that will represent the discrete set of data. So yun yung goal natin. Meron tayong discrete data. So we'll try to use numerical analysis tools in order to build up a nicely behaved function that will represent this data. And once we have that function, we'll be able to apply those things that we learned from calculus. And then that's what I expect from you guys after the week. Bibigyan namin kayo ng data, and then we'll ask you to use things that you have learned from calculus in order to make sense or to get something out of these data sets. Okay? But again, the first order of business is to create such a function that represents these data. Okay? Okay, so basically this is a common mathematical problem. So if you have a discrete set of data, meron kang x1, f of x1, x2, f of x2, and so on, where the exabytes are distinct values of the independent variable, then there are two possible cases. Number one, we want to approximate the value of f at some value of x not included in the list. So kung ang exabytes mo lang ay 0, 10, 20, 30, hanggang 50, what if you want to get the function value at say 45 or 37? Okay, so how do you predict what would be the value at an abscissa or an x value that is not included in the data set? Or another possible problem, which is much more general than the first bullet, is to determine a function g that mimics the behavior of the data in some sense. So gusto nating mag-build up ng isang function g that will sort of imitate how the function f behaves. And actually, it's a little bit ambiguous when we say mimics. So, ano yung ibig sabihin natin ng paggaya o pagkopya ni function g dun sa properties ni function f? And for that, there are two possible ways on how to create such a function g. So the first one is approximation, and the other one is interpolation. So when we say interpolation, so a function g interpolates a function f if we will require 0 errors at the nodes or the given exabytes. So usually I'll call the given exabytes as the nodes or the abscissas. Okay. Dun sa data set. And then if you want to interpolate the function f, then you will derive a function g which has 0 errors at the nodes. Ibig sabihin, sa bawat given x sub I, yung error ay equal kay 0. Because this makes sense, because if you have, say, if you already have a set of data, gusto mo yung function g na gumagaya kay f will exactly have the function values as in the given data set. So that's the interpolatory requirement. We want f of xi minus g of xi to be equal to 0, or the function g that mimics the function f must exactly have the function values given in the table for f. All right? And this is in contrast to approximation. In approximation, we don't care about the data sets, but we want to minimize some measure of error. And usually, this measure of error is global. Kasi pwede nyo tingnan yung error in approximation is local because we are imposing 0 error at specific data points. And these data points ay yung mga abscissas o yung mga nodes na given dun sa problem. Pero when you go into if you say approximation, this is much more general because we don't impose a very local measure of error. Pero gusto ko mag-minimize ng some measure of error which necessarily doesn't require 0 error at the nodes. So for instance, one such measure of error is this one, which is basically the least squares error. Gusto mong maliit yung sum ng total ng mga errors sa bawat exabytes. Okay? And these guys do not necessarily need to be equal to 0. We want them to be as little as possible so that you meet the error threshold epsilon. So that's why approximation treats error in a much global sense rather than a local sense. All right? So that's how we differentiate approximation versus interpolation. Sa approximation, gusto mo lamang humanap ng function g na kinokopya yung ginagawa ni function f, pero meron lang maliit na error. And the measure of error is subjective or can be selected ad hoc, depende sa kung ano yung gusto mo. But interpolation is a much more specific type of approximation, wherein the measure of error that we impose on the function g is having 0 error at the data nodes or at the interpolatory abscissas. Okay? So hopefully kaya niyong i-reason out pag nagpa-problem set ako. Pwedeng posibleng question number 1 is differentiate interpolation from approximation. So yun yung mga tipo ng mga tanong na makikita nyo sa mga problem sets. Okay? All right. So let's consider the function, the exponential function e raised to x. So if you have the function, an interpolating polynomial, kunwari, ang alam ko lang na data ay yung x and y values for x equals -2, -1, 0, and 1. So ito yung, pwede nyo sabihin, ito yung nodes or abscissas. So of course, you can get a table. So pwede kang gumawa ng table. Ito yung x, ito yung f of x. So -2, -1, 0, and 1. So you have e to the -2, e to the -1, 1, and e. All right. So if you want to interpolate the exponential function using the nodes -2, -1, 0, and 1, yung interpolating function g mo, dapat pag pin-log in ko si -2, si -1, si 0, at saka si 1, G should return exactly these three values. Okay. Now, in contrast, when I just ask you to approximate the function e to the x, then you can do so in several ways. The only requirement is that that function g must be very close to f up to some extent of a measure of error. Okay? Kaya makita nyo, napaka-restrictive nung interpolation. So, you will learn later that if I will use these abscissas or nodes, the interpolating polynomial for the function f is this polynomial p. So you can try. Pag pinlog in nyo si -2, ang magiging sagot na function value kay p ay e to the -2. If you plug in 0, p of 0 will be equal to 1. And so on for the other two interpolatory abscissas. So lagi siyang magpa-pass through dun sa given abscissas. Okay? While an example of an approximating polynomial for f is this guy. Do you guys remember what q is? Alala niyo pa ba? Ano yung saan ko nakuha itong approximating polynomial q para kay f? Do you still remember? Anybody?
I think there's a Taylor. I think this is the Taylor. Taylor's theorem pa?
Okay.
Yung
Tama ba si
Taylor
David ba yung
series
sumagot?
approximation.
Yes, that's right, David. And Chazelle is also right. This is a truncation of the Taylor series expansion. So, ang e to the x kasi sum siya ng x to the n over n factorial. So, and then probably, yeah, that's one way to approximate any function f, any nicely behaved function f, using its Taylor series expansion. But if you plug in, say, if you plug in 1, kinuha mo yung q of 1, yung q of 1 ay 1 plus 1 plus 1 half plus 1/6. Obviously, this cannot be equal to e, all right? But if you plug in 1 to p, ang makukuha natin dyan ay e to the first power, or e. So ito yung main difference between interpolating polynomial and approximating polynomials or approximating functions. Now, I think I illustrated that here. Hindi pala. Sorry. Let me switch to the module. So I guess here, okay, here you go. So to better illustrate it, let's look at figure 1 on your modules. So here I plotted e to the x against the interpolating polynomial that we have seen earlier. So kung makikita nyo, magi-intersect yung e to the x, which is the blue curve, and the interpolating polynomial, which is the red curve, at the interpolatory points. So yung intersection nila ay na-color ng black. Or if they almost intersect with each other, makikita nyo yung color black na lang. So you see, magpa-pass through siya dun sa lahat ng 4 na interpolatory abscissas o dun sa given na data points dun sa data. Remember, ang data ko lang dito ay kapag x ay -2, -1, 0, and 1. And again, being an interpolatory polynomial, this guy will intersect the blue curve at the 4 points that were given as data. Okay? So makita nyo, maganda yung interpolation at yung approximation, at least on this portion. Because after that, medyo lumalayo na yung red dun sa blue curve. Okay? And we'll say something about that later. And then if we look at the Taylor series expansion, here's the approximation we use by truncating the Taylor series expansion for e to the x. And you see here the starking difference between interpolation and approximation. Remember, we treat x equals -2 to be a data point, right? So, but however, the interpolating polynomial, the approximating polynomial doesn't pass through -2 comma e to the -2. So hindi sila nag-intersect dito. All right? Because in approximation, we don't care or we don't require passing through the given abscissas or the given points in the data set. Okay? Though makikita nyo, maganda pa rin naman yung approximation, at least on this interval over here. Okay? But I guess you remember that if you want to have better approximation using the Taylor series expansion, you will need to use much more much more terms in your expansion. Okay. So let me go back here. Sorry, medyo pa lipat-lipat ako, but okay. So why focus on interpolation? Well, interpolation actually is a very, it's a very simple process, and it's easy to implement using a computer, or actually even by hand, especially if you have a very small data set. So here are some common forms of interpolation. So there is a polynomial approximation, there is a piecewise polynomial approximation, and we will cover both of these in chapter 1. But some other types of interpolation, you have rational interpolation, you also have trigonometric interpolation, and I guess there's another one, exponential interpolation. But again, we will limit our discussion to the first 2 bullets. If you want to do a project later, you can take a look. You can take a look at rational, trigonometric, and exponential interpolation. Pwede nyo siyang gawing topic for the final project in our class. Okay, but again, we'll focus on the first 2 bullets. Now, why? Why focus on these 2 guys? Well, these 2 types of interpolation involves polynomials. What's the nice thing about polynomials? Well, polynomials are the simplest kind of functions, and they're practical for computers. Bakit? Kasi polynomials, if we want to evaluate polynomials, we only need to perform the 4 basic operations: addition, multiplication, subtraction, and division. And that's it. And they are very practical for use on computers. Second is that the derivatives and integrals of polynomials are easily computed. Meron na tayong shortcut or theorems from calculus that allows us to find the derivatives and integrals. And even more than that, their derivatives and integrals are still polynomials. So kung kailangan ko sa application ko ng derivative at integrals, madali silang computein. And what I get back would be again a polynomial, which is again practical for computer implementation. So kaya mas gusto natin na gumamit ng polynomials in interpolation. And they are differentiable infinitely many number of times. So pwedeng paulit-ulit kang mag-differentiate. Okay. And then this is one very classic result. Kasi for any required accuracy, lagi kang may makukuhang polynomial na nag-approximate kay f. All right. So, ibig sabihin, and actually this is contained in what we call the Weierstrass first approximation theorem. Okay, so which is one of the objectives of the class. So you should be able to state this theorem because this is a very classic result. Though the proof is a little bit more technical for the course, so we'll omit the proof. Okay, but what does the first approximation theorem tells us? It tells us that for any continuous function f and any epsilon greater than 0, we can always find a polynomial p such that the difference or the absolute difference between f and p is less than epsilon for every x in the interval ab. So sinasabi lang ng Weierstrass first approximation theorem, if you have a continuous function f on the interval ab, then it is guaranteed that for any level of precision or accuracy, lagi kang may mahahanap na polynomial na p ng error compared kay f ay napakaliit, or it will satisfy your error threshold epsilon. Okay, so it doesn't matter how crazy your polynomial f is on the interval ab, as long as it is continuous, you can approximate it by a polynomial. Kaya naman mag-stick tayo sa polynomial sa approximation kasi guaranteed na lagi tayo may mahanap na polynomial approximant for a certain function f, as long as your function f is continuous. Alright? Kaya hindi tayo mauubusan. Sabihin nyo, sir, hindi pa pwede mag-polynomial approximation for this function. Kasi because of some other reasons. But Weierstrass first approximation theorem will tell us na hindi. Lagi kang may mahanap na polynomial. Galingan mo lang yung paghahanap. All right. Now, okay. So I guess we are ready to take a look at algebraic interpolating polynomials. So here I will define formally what an algebraic interpolating polynomial is. So polynomial P sub n of x, all right? So which is computed using your indeterminate x, the function f to be interpolated, and the set of all x subies that will be used. So ito yung kailangan natin para ma-compute ang isang interpolating polynomial. Right? These are the parameters of our interpolating polynomial. Now, this interpolating polynomial is of degree no greater than n. And that is the purpose of the parameter n. Si n yung maximum degree possible for your interpolating polynomial. And it is also 1 less than the number of data points used. So kung meron kang n plus 1 na data points na pwedeng gamitin, then what you'll get back in your interpolating polynomial is a polynomial of degree no greater than n. Pwedeng mas mababa sa n pero hindi lalampas. So if you have 3 data points, so you can get a polynomial of degree at most 2, and so on. Okay. And this is a polynomial of this form, so nothing fancy here. This is your usual form for a polynomial. But again, we are defining an interpolating polynomial, so I should have here the interpolatory requirement. And the interpolatory requirement is that the function value of p should coincide with the function values of f at the given abscissas x1 until x sub n plus 1. So in short, we want p sub n of xi to be equal to f of xi for all I from 1 until n plus 1. So dapat parehas sila ng function value sa lahat ng given x1 until x sub n plus 1. Kaya kung makikita nyo, lahat ng parameters dito has their own purpose, right? X, of course, your indeterminate variable. Si f, yung function to be interpolated. Tapos ito yung mga x subies dun sa dataset. And of course, we also have here the degree. So yeah, those are the purposes of these parameters. So here I just defined what the AIP is, or the algebraic interpolating polynomial, but I haven't said paano natin to mako-compute. Okay? Or will it always exist for any set of abscissas and the function f? Actually, that is guaranteed by what we call the unisolvence theorem. Because this is a very powerful theorem because it tells us na hindi lang nag-exist yung algebraic interpolating polynomial, pero siya ay unique. So there is a unique algebraic interpolating polynomial. So if we want to prove the unisolvence theorem, it should be of 2 parts. First is a proof for existence, and second is a proof for the uniqueness. Let me see if I prove that here. Hindi ko na siya pinrove dito, so punta na ako sa module. Kasi dun sa module, I included the proof here. Okay. All right, so the unisolvence theorem is theorem number 2 in the module. And as I've mentioned, we need, if we want to have a proof for it, we need to prove 2 statements. Number 1, the existence of the algebraic interpolating polynomial and its uniqueness, okay? Now let's start with the existence. So here, I am claiming that this function here is an algebraic interpolating polynomial for the function f, okay? Here, the little l subcase are given by this function, okay? Now, we usually call the little l to be the Lagrange basis polynomial. Okay. And let's see if it is indeed a polynomial. So here, it is just a product, okay? Product ng mga ano, it's the product of x minus x sub I all over x sub k minus x sub I, where I goes from 1 until n plus 1. but provided I not equal to k. Dali naman tandaan na I cannot be equal to k kasi otherwise magzi-zero yung denominator. So kunin mo lang pala yung x minus yung mga x of I and so on. Pero wag mo isama si x of k kasi lahat sila ay may denominator na x of k minus x1, x of k minus x2, and so on. Magzi-zero yung denominator. Okay? And let's check if it is a polynomial of degree no greater than n. So if you look at this, ilan yung makukuha kong factors dito? If I'm taking the product from 1 to n plus 1 of factors of this form, provided I not equal to k, so ilang factors meron si L sub k? Or do you want me to enlarge this? Yeah. Anyone? Ano yung degree ni LK? So again, we can find the degree of LK by looking at how many factors do we have. Kasi may x ka lang naman dito, mag-multiply ka na mag-multiply. So kung ilan yung pinag-multiply natin ng mga x minus xi over xk minus xi, yun yung degree ng Lagrange basis polynomial. So can anyone tell me how many factors or what is the degree of LK? Actually, nandun na sa module yung sagot, no? Pero assuming di nyo pa siya nababasa.
Sir, nakalagay po dyan na degree n siya. Kasi po from 1 hanggang n plus 1, except yung sa
Okay.
k po. So, bale. And I think tama po ba k is between 1 and n? Di n lang po natira. So, n
Okay.
degree po siya.
Yeah, thank you, David. That's correct. Makita nyo, lahat ay pinag-multiply ko. Bawat isang xi, magkakaroon siya ng isang ganitong factor. Kasi papag-multiply ko silang lahat. Pero provided that I is not equal to k. So for every k, LK will have n factors. Alright? So ibig sabihin, ito ay degree n. So bawat LK ay degree n, tapos yung f of x of k ay function values lang naman. So mga constants yan. So si P ay sum, okay, ng mga function value, mga constant, times polynomial of degree n. So ibig sabihin, P should be degree n. Alright? So hopefully you see why that is true. And then, so okay na. So si P sub n ay polynomial of degree not more than n. So we only need to check na satisfy ba niya yung interpolatory requirement. And to do that, let's look at the Lagrange basis polynomial. So ito si LK. And then let's take an xj. J is a number from 1 to n plus 1. And then let's evaluate what's L sub k of x sub j. So isipin nyo lang si x sub j, isa siya dun sa mga abscissas na given dun sa problem. Okay? So pag binuo ko si x sub k, ganito yung itsura niya. Okay? Product ng mga xi minus xj, product ng x minus xi over xk minus xi provided I not equal to k. So ito yung magiging itsura niya. Tapos ipin-log in ko lang si xj. So kung meron siyang x dito, ipa-plug in ko si xj, makukuha ko to. Okay? And then let's see what happens. Well, kapag ka si j ay not equal kay k, anong mangyayari? So mangyayari is, so okay, umpisan siguro natin sa k equals j. If k is equal to j, ibig sabihin ito ay j, ito ay j, ito ay j, ito ay j, ibig sabihin lang lahat ng ito ay magiging equal kay 1, right? Kasi yung denominator magiging exactly the same as their numerator. So if k is equal to j, then 1 lang yung value ng Lagrange polynomial. But if k is not equal to j, bakit kaya siya magzi-zero? Any guess? Why will this be equal to 0 when k is not equal to j? Bakit kaya siya magiging 0 kapag ka si k ay not equal to j? Alright, so if k is not equal to j, ibig sabihin meron dito na x minus xj over xk minus xj. Tama? Kasi sa Lagrange sa Lagrange basis function, kapag ka si I ay not equal kay k, meron kang factor na ganito. So if j is not equal to k, then L sub k will have this such factor. Okay? Kasi nga j not equal to k, so dapat isa sa mga factors na to ay x minus xj over xk minus xj. But what will happen if I plug in xj into it? So kung magpa-plug in ako ng xj, x will become xj. I will have xj minus xj over xk minus xj. So meaning this will become 0 when x is equal to xj. So isa sa mga factors na nandito will be 0. And then 0 times all other factors will give us 0. Okay? So probably kung mahirap siya makita with all these parameters, maybe in an example later we'll see why this happens. But if you will try to do the calculations carefully, you'll get that it will definitely be equal to 0 when k is not equal to j. All right? And then makikita natin na, all right, so take note of this. When I do plug in xj into p sub n, okay, plug in ko lang siya. Kapag ka si j ay hindi equal kay k, ibig sabihin, magzi-zero yung Lagrange polynomial. So nasan ba si j? So nandito si j. Okay? So ito yung f of xj times the Lagrange j xj. Okay? At sabi natin kapag ka si k ay equal kay j, yung Lagrange polynomial ay 1, i-multiply ko lang ng function value kay xj. But the rest, it would be f of xj times lk or L1 of xj. Pero since j is not equal to 1 kasi nandito pa si j, magzi-zero siya. And then since j is not equal to 2, at least in this expansion that I have over here, merong f of x2 times 0. Tapos if I am at j minus 1, L sub k of x sub j minus 1 will be 0 times the function value, magzi-zero siya. So laging Lagrange polynomial or Lagrange basis polynomial ay nagiging 1 lang kapag kay xj. So kaya siya lang yung magkaka-non-zero multiplier, and then when you sum these things up, you'll get f of x sub j. So dapat to ay subscript. So let's change it to subscript. And that's it. P sub n of xj is equal to f of xj. And this is true for all j from 1 to n plus 1. So therefore, the interpolatory requirement is satisfied. Okay? Now, we are done with existence, and actually this proof gives us a way on how to write the interpolating polynomial. We'll see that later, okay, in action. Now let's prove uniqueness. So this is a usual proof of uniqueness. We assume otherwise. Kunwari, meron dalawang algebraic interpolating polynomial. Let's say si P at saka si Q. All right? So gusto ko ipakita ngayon that P is necessarily equal to Q to prove uniqueness. Okay? So in order for me to show that P and Q are the same, I will define a function R such that it is the difference between P and Q. Okay? So dahil si P at saka si Q ay degree n, or degree no more than n, so ang degree ni R is also less than or equal to n. Tama? So si P ay degree n or less, si Q ay degree n or less, so R must be degree n or less. Okay, I hope you agree. But if I plug in x sub j, all right, to R, this is basically p of xj minus q of xj. Pero parehas silang interpolatory polynomial. So ang p of xj ay equal kay f of xj. Yung q of xj ay equal kay f of xj. And then when I subtract them, 0 yung sagot. And this is true for all j from 1 to n plus 1. And I say that's a contradiction. Bakit kaya may contradiction doon? Any idea bakit kaya may contradiction? Or wala pa kayo nakikitang contradiction?
Sir, dahil po ba bawal mag-zero yan? Kaya siya nagko-contradict?
Pwede siyang mag-zero. Pero ang problema ko dito, actually, I think you're on the right track, David. Thank you for suggesting that. The reason here is by the fundamental theorem of algebra. Tandaan nyo ba yung fundamental theorem of algebra? Okay, nalimutan nyo na siya. Sabi ng fundamental theorem of algebra, kapag ka meron kang degree n polynomial, meron kang at most n roots. Tama? So kung meron kang x squared at most 2 roots, meron kang x cubed at most 3 roots, meron kang x to the 50th, meron kang at most 50 roots. All right? But we have mentioned here that R is degree no greater than n. Kaya lang, ilan yung roots na nahanap natin? Ilang x's at least yung nahanap natin na nagpapa-0 kay R? So we have x1, x2, x3 until x sub n plus 1. So ibig sabihin si R ay isang polynomial na merong n plus 1 roots. Pero sabi ng fundamental theorem of algebra, if you have a non-zero polynomial of degree n, then it will have at most n roots or n zeros. But here we got a polynomial of degree no more than n, pero it has n plus 1 roots. So therefore, R must be the zero polynomial. Otherwise, mababiolate yung fundamental theorem of algebra. So that's why we can say that R must be equal to the zero polynomial, okay? But R is also px minus qx. So px minus qx must be equal to 0, or in other words, p must be equal to q. All right? And so the interpolating polynomial is unique. Okay? Does the proof make sense? O may malabo bang part? Wag mahiyang magtanong. Any questions? No questions? May malabo pa? Yes.
Pwede paki-explain ulit yung bakit may contradiction, sir? Kasi medyo malabo yun sa akin.
Okay. So, ang contradiction is a fundamental theorem of algebra. So, ang fundamental theorem of algebra says, let P be a non-zero polynomial of degree n. Then P will have at most n roots. So ito yung probably nakita nyo to sa Math 111 o kaya sa actually kahit sa high school algebra. Na pag meron kang polynomial na degree niya ay n, ibig sabihin makakahanap ka lang ng at most n na roots or n na zeros. So ibig sabihin si P can only be equal to 0 for at most n values of x. Bawal lumampas sa n. So yung degree hindi pwedeng mas maliit kaysa dun sa number of roots. Okay? So kaya lang, dito sa function r natin, alam natin si r, ang degree niya ay mas maliit kay n or equal kay n. Okay? It's a degree n polynomial at most. Pero, nakahanap tayo ng n plus 1 na roots kasi pag pinlog in ko kay r, yung mga exabytes na ginamit dun sa interpolation, j going from 1 to n plus 1. So bawat isang xj, pag pinlog in ko kay r, ang sagot ay 0 because of this thing. Right? So that makes each of the x sub j's to be a root of the polynomial r. Okay? But there's a problem there. R is at most degree n, okay? And yet, we found n plus 1 roots for it, which precisely are the abscissas used in the interpolation process. So degree n polynomial at the most. Pero meron siyang at least n plus 1 roots. So nava-violate niya yung FTA. And that means we are forced to say that the polynomial r is actually the zero polynomial. Otherwise, mako-contradict si FTA. So we must admit that r of x must be equal to the zero polynomial. Oh, sorry. I should have it here. Okay. R of x should be equal to the zero polynomial. And being the zero polynomial, pero si r dinefine ko to be p minus q. Eh, lagi naman siyang zero daw, kahit anong x pa yung i-plug in ko. So that means p must be equal to q for any x. And hence, I cannot get two different interpolating polynomials. Because if p and q are interpolatory polynomials, then they must be equal to each other. Okay? Is that better?
Yes, sir. Thank you, sir.
All right. Okay, let me borrow 5 more minutes and let's try to see this in action. So the beauty of the proof is that it's not just on its theoretical aspect. It guarantees there will always exist an interpolating polynomial, and that interpolating polynomial will be unique. But the nice thing about the proof, it gives us one way to compute the interpolating polynomial. And that's what we call the Lagrange form. Okay? So para mabuo yung interpolating polynomial, computean mo lang yung mga Lagrange basis polynomials, i-multiply mo bawat function value, i-sum up mo sila, you'll get the interpolating polynomial. So let's see this in action probably. Let me mention 2.1 later, but let's see. Okay. Example 1. Let's find the interpolating polynomial for the points 1, 1, 2, 4, and 3, 9. Of course, if you look at the data set, you will have an idea. So mukhang yung function f ay x squared, right? Say 1, 1, 2, 4, and 3, 9. But let's see if we will get that. So if I ask you to get an interpolating polynomial, here you note that, oh, I have n is equal to 2. Kasi this would be x1, this would be x2, this would be x3. And remember, yung last term, dapat siya yung x sub n plus 1. So that means n is equal to 2. So here I am expecting a degree 2 polynomial or less. Okay? Kasi meron akong 3 data points, so laging minus 1 yung maximum degree. 3 data points, I will have an interpolating polynomial of degree at most 2. Okay? And how do I get that? Well, sundin nyo lang yung formula ni Taylor. Yung function value, i-multiply mo sa Lagrange polynomial. So let's try to build the first Lagrange polynomial. Ito muna ang Lagrange polynomial. So here, k is equal to 1. So kailangan ko lang daw gawin, x minus lahat ng x sabays, maliban dun sa x1. Right? So I'll have x minus 2 over 1 minus 2. Kasi remember sa Lagrange ay yung denominator ay xk minus x1. Okay? So here, this is actually L2. Actually, hindi na nga siya L2 eh. So yung mga denominator ay laging yung x sabay. So ito yung para kay x1. Okay. Yung mga denominators laging x1 minus xk. So here I'll have x1 minus, hindi ko pwedeng lagyan ng 1 minus 1 yung denominator. So kaya laging dalawa lang yung multiplier. So I have x2 over 1 minus 2 times x minus 3 over 1 minus 3. Saan nanggaling si 2 and 3? Kasi sila yung x2 and x3. So ito yung x2, ito yung x3, tapos ito ay x1. Okay? Tapos ang requirement sa L sub k, bawal yung magkaroon ng x1 minus x1 sa denominator. So basically this is your L1. Okay? Which is the product of x minus xj all over xi minus xj. Okay. And then, i-multiply mo yan ng function value. The first function value, the first data point is 1, 1. So yung multiplier na 1 nanggaling doon. Okay. And then if we'll go to the second term, so this guy should be L2. So ibig sabihin lahat ng mga x sub j, basta hindi equal si j kay 2 ay magkakaroon ng representative dun sa L2. So here I will have x minus x1 over x2 minus x1 times x minus x3 over x2 minus x3. Hindi pwedeng isama yung x minus x2 kasi yung denominator nun ay x2 minus x2. So, kaya hindi siya, kaya dalawa lang talaga lagi yung factors. And then if you plug in x2 here sa mga denominators, x2 is the second abscissa, which is just 2. So that's how we got the L2. And then yung f of x2 ay yung function value lang nung second abscissa. Kaya siya nandun. And similarly, the third term, this is x minus x1 all over x3 minus x1. And this is x minus x2 all over x3 minus x2. And then if you simplify this, you will get x squared as what we predicted before. Okay? Clear ba yung pag-follow ng process? I included example 1 here kasi madali siyang sundan manually. So, unfortunately, we're running out of time. So you can try examples 2 and 3 on your own time, probably if you'll get some time later. So in this particular case, you will see in example 2, we have how many points? We have 4 data points. So we are expecting a polynomial of degree 3. All right, but you will see that the answer is a polynomial of degree 2. Just to illustrate the fact that hindi laging nakukuha yung eksaktong expected maximum degree. Again, if I got cut off, I was saying that in example 2, we have 4 data points. So we expect a polynomial of degree at most 3. All right. But if you try to use the Lagrange form, you will get x squared again, which is a polynomial of degree 2. That is still fine because all the unisolvents theorem promises us is that you will get a polynomial of degree at most 3. And here we get a polynomial 2, which is still less than or equal to 3. Kasi kung makikita nyo, parang redundant yung dinagdag ko na pang-apat na data point because 4 and 16 para pa rin siyang x squared. So probably that's what you can do during your free time. Try to use the Lagrange form. Be familiar with it and try to recover what I got in example 2. And probably you can also try example 3. Okay, but maybe I'll say a couple of words about these 2 examples before I go to the more exciting problems, examples 4 and 5, which we can discuss on Thursday. And I will use MATLAB to illustrate how to use a software in order to get the interpolating polynomial. Okay. So, kasi mas exciting yung problems 4 and 5. But I hope you can try on your own, at least manually, examples 2 and 3. All right? So, any questions? Anything you want to share for now? Masyado ba mabagal? Parang nabagalan ako sa discussion ko kasi supposedly dapat matapos ko yung examples 4 and 5 today.
I think okay lang naman po yung pace, sir, kasi medyo nakakalito intindihin po yung Lagrange basic form po.
Yung basic form, yeah. Especially if you're seeing it for the first time.
Okay.
So that's why I suggest, at least if you find some free time, try to use definition 2.3, get the Lagrange interpolating polynomial, and derive back what I got from examples 1 to 3. Probably you can start with example 3 kasi mas maiksi siya. Dalawa lang yung data points. So makukuha nyo ay linear o kaya constant polynomial kasi degree at most 1 yung makukuha nyo. Then you can jump on example 2. And then yung example 3, yung example 1 medyo na naumpisahan ko na naman. So that pagpunta natin on Thursday again on the class, we can tackle the more exciting problems. So we'll go back to the epidemic problem. We sought the introduction and also the pricing problem, example 5. And again, for this, I'm going to use MATLAB. So if you guys don't have MATLAB yet, you can download MATLAB para makasunod kayo on Thursday. Pero hindi naman required na MATLAB yung gamitin. Pero MATLAB yung gagamitin kong pang-illustrate sa klase. Kasi ito yung lahat tayo supposedly may access. Because this comes free with a university subscription. Okay? So any other questions, parting words? Wala naman. The proof might be too technical for you, especially if it's the first time, but hopefully if you reread it later, if you will realize some questions or if something is not clear again, just let me know on Thursday. But are there any questions? Kung wala naman, then let's call it a day for now. So thank you for coming today. Enjoy the rest of the day. And let's see each other again on Thursday. Bye, everyone.
Thank you, sir. Bye po.
Thank you, sir.
Po.
Okay.